Today we'll cover section 3.2 in our continuing study of logic. 3.2 is called Truth Tables, Equivalent Statements, and Tautologies. In the previous section, we learned that truth tables are used to list every possible way that a simple or compound statement can be true or false. And we covered two of what will eventually be 5 basic truth tables whose values will allow us to tackle many more complex logical statements than we've done so far. So these are the two we've already covered. The conjunction, which is the and we learned that an and is only true when they're both true. And the disjunction, or the or, and we learned that a disjunction is only false when they're both false. True when they're both true, that's and. False when they're both false, that's or. Those little memory aids help you remember what the table values are without having to strictly memorize the tables themselves. We're going to add a third one now called the negation. The negation of a statement P is tilde P, or it's just a squiggle, tilde P, and of course it has a truth table as well, and it simply changes the truth value to its opposite. The negation changes the sign. The negation changes the value of its truth value to the opposite. So the negation is false whenever the original statement is true, and is true whenever the original statement is false. So our little memory aid is for a negation, true becomes false and false becomes true. For example, if the statement said the ball is red, the negation would be the ball is not red. If the original statement is true, that is, the ball really is red, then the negation is false, which says the ball is not red. On the other hand, if the original statement is false, then the negation is true. It simply changes the truth value to its opposite. Notice that manipulating logical statements is a lot like using the English language. For example, if I ask you, "What is your name?" you must analyze the sentence in order to properly respond with your name. Perhaps my name is Laura, my name is Tom, whatever your name is. Similarly, if I give you the logical statement T and F, you must analyze it in order to give the proper response, which of course is false. So there's a really close analogy with the English language here if you think about it. When you're doing this sort of thing, you might say that you're operating in interpretation mode. You're interpreting what the symbols mean. When operating in interpretation mode, we use basic rules to tell us how to respond to the logical statement, for example, T and F. The basic rule we need here to interpret it is that it's only true if they're both true. Well, they're not both true here, so that tells you that the result is false or the answer is false. So when we operate in interpretation mode, we're just using a basic set of rules to simplify a logical statement. For example, I might ask you to construct a truth table for the statement P and not Q. What you typically do is make a P column, a Q column, where you have all possibilities. Both P and Q could be true. Each one of them in turn could be false, or they could both be false. And then to make it easier, most people do this by adding columns that correspond to the pieces of the complete compound statement. So I see a not Q to the right of the and, so I'm going to create a not Q column. And eventually I want to do P and not Q as a whole statement, so I'll make a column for that. So you can sort of see you start off with the P and Q columns, then you look and see the pieces. There's a P piece, but you've already taken care of that. There's a not Q piece, so you put that in there, and then the whole statement gets its own column. It just makes it easier if you do it that way. Because you'll see as we go through this, if I want to do this, the first thing I want to do is fill in the values for not Q, and in order to fill in the values for not Q, I have to look at the Q column. And remember, the not is the negation, which changes the truth values. So true becomes false, false becomes true, true becomes false, and false becomes true. And notice I'm looking at the Q column to figure out what not Q is. Now that I've done that, I move to the last column, and the last column has a statement P in it. So what I can do is just lift the values of P on the far left and just transfer them over under the P in the last column. And then I can do the same thing with the not Q. I see on the other side of the and there's a not Q, so I can simply lift those values and slide them over under the not Q. And notice that between those two things is an and symbol, so I'll just push the and all the way down. And now I need to evaluate the and in that last column. Remember that a conjunction, which is an and, is only true if both statements are true. So if I look at the first one, they're not both true, so that means the statement is false. Looking at the next one, they are both true, so the statement is true. In the third case, they're not both true, so the statement is false. And in the fourth case, they're not both true, so the statement is false. So you go down there and you interpret and by remembering that it's only true if they're both true. And that gives you the complete solution for that truth table for that original statement. Pretty simple if you take it one step at a time and create those intermediate columns when you need them. Sometimes we're asked for the truth value of a statement that doesn't require us to build the entire truth table. For example, this problem simply says determine the truth value of the compound statement given that P is a true statement and Q is a false statement and R is a true statement. And the logical statement is P or, and then you've got in parentheses, not Q or R. You don't have to do the whole truth table if they tell you that P is true, Q is false, and R is true. All you need to do is note that P is true, Q is false, R is true, and then plug in a T for the P, plug in an F for the Q, and plug in a T for the R. And if you do that, you get the statement true or, and in parentheses, not false or true. And once you do that, you can work your way through. And notice you want to get rid of that negation first. That's probably what you want to do. Notice that not false is true. So that statement turns into true or, and in the parentheses, true or true. From there on out, you want to work inside your parentheses first. True or true is true. And then you're left with true or true, and true or true is true. Remember, with or, it's only false if they're both false. So you end up with a statement value of true. And notice you didn't have to produce the entire truth table if you already know the values of each individual statement. By the way, there's a name for a statement that's always true. It's called a tautology. And here's an example to work through. You're going to see that this statement is actually a tautology. It's always true. Let's just do it with a truth table. Add the extra columns. Remember, you're going to start out with a P column and a Q column with every possible combination of true and false. You notice up there there's a not P inside of the whole statement, so you make a not P column. And then on the left there's a P or Q, so you'll make a P or Q column. And then you'll want a column at the end that encapsulates the entire statement. And from there you just move from left to right. So I'll start off, I form the not P column by taking the opposite truth value of the P column. So if P is true, not P is false, and so on down the line. That gives me not P. Then I move to the next column and notice that there's a P on one side of the OR and a Q on the other side of the OR. So I'll just take those P values and move them underneath the P values in that middle column, and then I'll take the Q values and move them underneath in the Qs. In the first row, that leaves me true or true, true or false, false or true, and false or false. Now remember, with an or, it's only false if they're both false. So I might notice there's only one place where they're both false. You might just notice that that's first and the rest of them have to be true. If you can identify the false one, the rest of them have to be true, or the false ones had there been more than one. And so there you go with the P or Q column. Now you want to keep moving to the right, and you notice that for this last column, you have the P or Q done, so just transfer those values over. True, 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 false, underneath the P or Q. And you already have not P done in an earlier column, so transfer the not P values over underneath the not P. And remember, it's an or in the middle. So we're doing or again, and an or is only false if they're both false. If you look through there, there is absolutely no place where they're both false. So that means they're all true. Hence the name tautology. And a tautology is a logical statement that's always true. By the way, if they all turn out to be false, it's called a self-contradiction. If they're all true, it's a tautology. If that last column turns out to be all false, it's called a self-contradiction. Another thing about these truth tables, you can tell how many rows they're going to be by looking at how many distinct, simple, logical statements there are. In fact, if there are n simple statements, there will be 2 to the power of n rows. For example, if you take this one, there's a P, there's a Q, there's an R. So there are 3 simple statements. So 2 to the third is 8, and that tells you you'll have 8 rows in the truth table. So if you had a case where you had a P, Q, R, and S, which would be 4, it'd be 2 to the 4th, which would be 16, and so on and so forth. So you can always tell how many rows your truth table will have by counting how many of these simple statements there are in the compound statement. Let's go ahead and complete the truth table for it. Again, my suggestion is to put in the columns for the intermediate steps. If you look back, you notice there's a not R in that bigger compound statement, so I'll actually make a not R column. You also notice there's a Q and not R. I'll make a Q and not R column. And of course, the last column is going to have the statement you're trying to get the truth values for. Now that I got there, I notice there's a not R column that I need to fill out. So if you sort of start on the left, I'll take the R column and change all the truth values to their opposites. True becomes false, false becomes true, all the way down. Then I move to the Q and not R column, which is the next column. Notice I already have a Q column, so I'll move the Q's underneath the Q's. And I already have a not R column, so I'll move the not R's under the not R's. And then I'll notice it's an and between them. Remember, for an and, it's only true if they're both true. So if you just go down and look, that first one's not both true, so that'll be false. There's a both true there, so that'll be true. That's not both true, so it'll be false. That's not both true, so it'll be false. That's not both true, so it'll be false. That is both true, so it'll be true. That is not both true, so it'll be false. That is not both true, so it'll be false. Finally, I move to the last column, and notice I have a P there, so I'll go back to the original P column on the far left and move it over under the P. Then I notice I have a Q and not R column, and I can move it underneath the corresponding statement. And then I notice there is an OR symbol between them. And remember, for an OR, it's only false if they're both false. So I scan through them. That's not both false, so it's true. True is not both false, so that's true. That's not both false, so it's true. That's not both false, so it's true. That is both false, so it's false. That's the only case when an OR is false, when they're both false. The next one is not both false, so it's true. The next one is both false, so it's false. And the last one is both false, so it's false. And there you go. You've done the truth table for that problem. On the actual WebAssign homework, sometimes these truth tables look slightly differently because they're going to ask you to do drop-down boxes to pick your trues and false. I want to show you what it might actually look like in WebAssign. You might get something that looks like that. So you've got to practice what this means. And part of it is probably pretty common sense. For example, that Q column is exactly what we were doing before. You simply take the Q values in column 2 and move them underneath the Q values in that last part. Same thing with not P. You've got to take the negation of P. So if you go to the P's and take their opposites, the true becomes false in the first row, the true becomes false in the second row, the false becomes true in the third row, and the false becomes true in the fourth row. So you're actually doing the negation in your head, and you're moving the opposite values over. Then you notice that they're asking you to and those things. In other words, there's an and between each of those true, false, false, trues, and all those combinations. So you want to do an and an is only true if they're both true. So you look there, that true, false is not both true, so it'll be false. The second one, false, false, not both true, so it's false. The third one is both true, so it's true. And the last one is not both true, so it is false. Now, notice here, once you've combined the Q's and the not P's to get the ands, those things that are highlighted right now, those two columns that are highlighted, they're essentially used up. You're only paying attention now to that false, false, true, false column because they've been combined together into that middle column. So what I think of is you're only looking at that false, false, true, false column until you get to the very end, because you're going to OR that with the not Q column on the very end. You could actually take a pencil or something and just mark them out because they're not relevant anymore. Only those shaded columns matter now, and I'm going to OR them. So I have to get that not Q figured out. Well, if Q is true, then not Q is going to be false. If Q is false, not Q is going to be true. If Q is true, not Q will be false. And if Q is false, not Q will be true. So now I'm ready to actually complete the OR with those two shaded columns. And remember, an OR is only false if they're both false. The very first row is both false, so that'll be false. The second row is not both false, that'll be true. The third row is not both false, so it'll be true. And the last row is not both false, so it'll be true. So that is your truth table for the original statement. Practice this, and if it becomes necessary, you can actually copy this down onto your paper so you can mark things out if you think that's helpful. To continue the language analogy, in addition to that interpretation mode where we use our basic rules to simplify logical statements, and something called the translation mode, which is nothing more than translating from logical statements to English sentences or vice versa, we also have special cases or rules, just like you have in English, that apply only in certain circumstances. For example, the I before E spelling rule in English. This sort of corresponds to it. There are similarly special cases or rules when you're working with logical statements, and one pair of special rules is called De Morgan's laws. And there are two of them. De Morgan's laws for statements says for any statement P and Q, the negation of P or Q is not P and not Q, and the negation of P and Q is not P or not Q. Now, it might look a little strange at first, but it's very easy to interpret this. In the first statement, it says that if you negate an OR statement, you get an AND statement. So the OR on the left side becomes an AND on the right side, and the tilde, the negation symbol, distributes through just like a minus sign would if you were doing regular algebra. So the negation of P or Q is the negation of P and the negation of Q. An OR becomes an AND, and the negation passes through like a minus sign. And on the next one, it says that if you start out with an AND, the negation of an AND becomes an OR. And again, the same idea. You start off with an AND on the left. If you negate it, you'll end up with an OR on the right. And the tilde, the negation symbol, just distributes through as if it were a minus sign. So the negation of P and Q is the negation of P or the negation of Q. OR becomes AND becomes OR, and the tildes distribute like a minus sign. So these are really easy to remember. De Morgan's laws can be used to restate certain English sentences in an equivalent form. For example, I might ask you to use one of De Morgan's laws to restate the following sentence in an equivalent form. It is not true that I graduated or I got a job. You need to think of this in terms of the symbols. The it is not true that is like the tilde. It's the negation. Notice that we're using the comma for grouping just like we have in earlier cases. So when that comma there means that everything to the right of comma is grouped together. So that I graduated or I got a job is essentially in parentheses. It's grouped together. So I graduated or got a job, that together is grouped because of that comma. And we've done that earlier, so it's the same idea. The comma is telling us to group everything on the other side together. If you think of I graduated or got a job, finding the negation of that, it's like the first formula. It's like the negation of P or Q. So that would be equivalent to the negation of P and the negation of Q. So the negation of I graduated would be I did not graduate. The negation of I got a job would be I did not get a job. And remember, the original OR, when it gets negated, becomes an AND. So the statement, it is not true that I graduated or got a job, is equivalent to the first one of De Morgan's laws, which allows us to reinterpret the sentence in an equivalent form as I did not graduate and I did not get a job. So that's an example of using one of De Morgan's laws to change an English statement from one form to the other. And in particular, that English statement was the negation of an or. And I won't do it here, but I will say that I could do another example where I was doing the negation of an and. It would work the exact same way, except the and on the left would become an or on the right, and I would still do the negations of the P and Q exactly the same.